Welcome to the podcast, everyone. Today, we're diving deep into the fascinating world of recommender systems, specifically exploring a new technique for optimizing embedding layers. Joining us is Dr. Xiangyu Zhao, lead researcher on the AutoEmb framework, and Dr. Jiang Tang, a leading expert in the field of recommender systems. Dr. Zhao, can you give us a brief overview of the paper and the problem it addresses?
Thanks, Samantha. Recommender systems are increasingly critical in today's online world. They power everything from movie suggestions on Netflix to product recommendations on Amazon. But creating effective recommendation models is challenging. One key challenge is how to represent users and items in a way that captures their unique characteristics. This is where embedding layers come in. In essence, they transform high-dimensional data, like user IDs or item descriptions, into lower-dimensional representations that allow the model to learn relationships and make accurate predictions. However, determining the right embedding size is crucial for optimal performance, and this becomes especially tricky when dealing with streaming recommender systems where data is constantly changing. Our paper focuses on addressing this problem with a new framework called AutoEmb.
That's a great introduction, Dr. Zhao. Dr. Tang, as a leading expert in recommender systems, can you provide some context on the importance of embedding layers and why existing methods often fall short in dynamic environments?
Absolutely, Samantha. Embedding layers are the backbone of modern deep learning recommendation models. They're effectively the language the model uses to understand user preferences and item attributes. Think of it like a translation from complex descriptions to simpler, more meaningful representations. However, traditional approaches typically use a fixed embedding size for all users and items, which can be problematic. In a real-world streaming setting where new users and items are constantly being added and user preferences are changing rapidly, a fixed embedding size may not be sufficient to represent everyone effectively. Some users might have a lot of data associated with them, and thus require a larger embedding to capture their full complexity, while others might be new and need a smaller embedding for the model to learn quickly. This is where the challenge of dynamically adjusting embedding sizes arises.
Dr. Zhao, can you explain how the AutoEmb framework tackles this challenge of dynamically choosing embedding sizes?
Sure, Samantha. AutoEmb takes a novel approach to automatically select different embedding dimensions based on user and item popularity. Let me break it down step by step. First, we start with a basic deep learning recommendation model, DLRS. A typical DLRS consists of embedding layers, hidden layers, and an output layer. The embedding layers map user and item IDs to low-dimensional vectors. The hidden layers perform nonlinear transformations on these embeddings, and the output layer predicts the user's preference for an item. However, the traditional DLRS architecture isn't designed to handle different embedding dimensions. To address this, we enhance the DLRS model by introducing a mechanism that allows us to work with multiple embedding spaces, each with a different dimension. For instance, we might have one space for small embeddings, one for medium embeddings, and one for large embeddings. Then, we introduce a component called a controller network. This controller takes the user or item's popularity as input and generates a probability distribution over these different embedding spaces. This distribution tells us how much weight to assign to each embedding space based on the user or item's popularity. For example, if a user is highly popular, the controller might assign a higher probability to the large embedding space, which has more capacity to capture the user's complex behavior. But if a user is new and hasn't interacted much, the controller might assign a higher probability to the small embedding space, which can learn quickly from limited data.
So the controller is essentially deciding which embedding space is most appropriate based on real-time data, right?
Exactly, Samantha. The controller is a key part of the AutoEmb framework, making it dynamically adaptive. But there's one more important aspect, the soft selection. Instead of just selecting one embedding space with the highest probability, we use a weighted average of the embeddings from all the spaces. This allows us to take advantage of the information captured by each embedding space without completely discarding the others. This soft selection makes the whole framework end-to-end differentiable, meaning we can optimize it using backpropagation, which is a standard technique for training deep learning models.
Dr. Tang, what's your perspective on this approach? Are there any potential concerns or challenges with using a soft selection approach?
It's a clever approach, Dr. Zhao. It's certainly a step forward in terms of flexibility and adapting to dynamic data. However, using a soft selection requires maintaining multiple embedding spaces, which can increase memory requirements. This is especially important to consider in large-scale recommender systems where resources are often a limiting factor. But the benefits of having multiple embedding spaces, especially for capturing diverse user behaviors, outweigh this drawback in many scenarios. I think the real challenge will be in effectively training and optimizing the controller network to make accurate decisions in real time. It has to learn the complex relationship between popularity, data availability, and the appropriate embedding size.
That's a good point, Dr. Tang. Dr. Zhao, can you elaborate on how the controller network is trained and how AutoEmb is optimized overall?
You're right, Samantha. Training the controller is crucial for AutoEmb's success. We use a technique inspired by differentiable architecture search, DARTs. Instead of directly searching for the optimal architecture, DARTs uses a gradient-based approach to train a set of weights that represent the architecture. We adapt this approach to optimize AutoEmb's controller network. The controller is trained on a validation set of previous user-item interactions, which allows it to learn the general relationship between popularity and embedding size. This is different from traditional DARTs, which is typically applied to discrete architectures for tasks like image classification. In our streaming setting, we need to continuously adapt to new data, so the controller is always being updated based on the latest interactions. We update the controller's parameters based on the validation loss, while the parameters of the DLRS model itself are updated based on the training loss. This process is iterative, constantly refining the model and its ability to select the right embedding dimensions.
So it's a kind of meta-learning approach where the controller learns how to learn the best embedding configuration based on past data, and it can then apply this knowledge to new data in real time.
Exactly, Samantha. It's a clever way to take advantage of previous data to improve the model's ability to adapt to new users and items. And the results show that this approach is highly effective.
Dr. Zhao, can you walk us through the key results of your experiments and how they demonstrate the effectiveness of AutoEmb?
Certainly, Samantha. We conducted extensive experiments on widely used datasets, including MovieLens 20M and the Netflix Prize dataset. We compared AutoEmb's performance to several baseline methods, including using a fixed embedding size, a supervised attention model, and a standard DARTs model. Across all datasets and different tasks, whether it's predicting user ratings or classifying them, AutoEmb consistently outperforms the baselines. It achieves lower mean squared error and higher accuracy, which demonstrates its effectiveness in improving the overall performance of recommendation systems. Furthermore, we analyzed the impact of user and item popularity on performance. We found that AutoEmb significantly outperforms baselines in cold start scenarios, where users or items have limited interactions. This highlights the importance of AutoEmb's ability to adapt to dynamic data and quickly learn from limited information. We also observed that AutoEmb's performance stabilizes with increasing popularity, showing that it effectively captures the complexities of more established users and items. We can see this clearly in the figures we included in the paper. The weights generated by the controller for different popularities show a clear trend. For smaller popularities, it tends to favor smaller embeddings, while for larger popularities, it shifts towards larger embeddings.
That's very impressive, Dr. Zhao. It seems like AutoEmb really shines in scenarios where data is constantly changing and where new users and items are being introduced frequently. Dr. Tang, what are your thoughts on the broader implications of these results for the field of recommender systems?
It's certainly a significant step forward, Samantha. AutoEmb's ability to dynamically adjust embedding sizes opens up a lot of possibilities for building more adaptive and efficient recommender systems. In the past, we've relied heavily on static models that were often difficult to update in real time. AutoEmb tackles this challenge head-on, and its success highlights the importance of incorporating AutoML techniques into recommender systems. We're seeing a shift towards more flexible and self-learning systems, and AutoEmb is a great example of that trend.
I can see how this framework could revolutionize the way recommender systems are developed and deployed, especially in today's fast-paced online environments. Dr. Zhao, what are some of the limitations of the current AutoEmb framework, and what are the potential directions for future research?
You're right, Samantha. While AutoEmb shows promising results, there are certainly areas for improvement. One limitation is that the soft selection approach, while making the framework end-to-end differentiable, requires maintaining a larger embedding space. This could be a concern in resource-constrained environments. We're exploring ways to achieve similar performance with a hard selection approach, which would potentially require less memory. Another area for future work is to investigate different controller network architectures and explore more sophisticated methods for training them. While the current darts-inspired approach works well, there might be even better ways to optimize the controller's ability to learn the relationship between popularity and embedding size. Ultimately, we'd like to explore the potential for automatically designing the entire DLRS architecture, not just selecting the embedding dimensions. This would be a significant advancement for the field of AutoML in recommender systems.
Dr. Tang, what are your thoughts on the future of AutoML in recommender systems? Where do you see AutoEmb fitting into this evolving landscape?
I'm excited about the future of AutoML in recommender systems. It's an area with a lot of potential for creating more intelligent and self-adaptive systems. AutoEmb is a great example of how AutoML can be applied to optimize key components like embedding layers. As the field advances, we can expect to see AutoML techniques used to design and optimize entire recommendation models. This could lead to systems that learn and adapt much more effectively than current approaches. We'll need to address the challenges of computational cost, explainability, and data efficiency, but the potential benefits are enormous. AutoEmb is a fantastic first step in this exciting direction, and it's going to be interesting to see how this research evolves in the coming years.
Thank you both for this insightful discussion. It's clear that AutoEmb represents a significant advancement in the field of recommender systems, particularly for dealing with the challenges of dynamic data and streaming environments. It's exciting to see how this research can contribute to the development of more sophisticated and adaptive recommendation systems in the future.